Okay, in this video we're going to introduce the RSA cryptosystem. This is a real practical cryptosystem, unlike the polyalphabetic and monoalphabetic systems we've been talking about, which are educational but not very useful because they're too easy to crack. This one is a difficult one to crack, and it's used in commerce and secure communication over the internet, very widely used system. Now, the purpose of RSA is to enable secret messages that only one person can decode. So many people can send secret messages, and they can send them openly, but only one person can decode. Now, how does this work? All of these people who send, they must be able to know what's called a public key, which enables you to encode the message. Okay? But only one person can decode, only one person possesses the secret key. All right, so to create a RSA system, you need to be able to produce a public key and a secret key, or also called private key. Okay, so the key to constructing an RSA system is the construction of a public key and private key. Now, the process of producing these keys is outlined here. First, you choose two random 150-digit prime numbers. All right, now, of course, this doesn't seem very easy, but there are ways to do this. We may get into this later in this later section. Now, this next step might be unmotivated, but we'll talk about it a little bit later. Compute the product PQ, which is the product of your two prime numbers, as well as P minus 1 times Q minus 1. Now, why do you take P minus 1? It turns out that P minus 1 is actually the number of integers less than P that are relatively prime to P. Q minus 1 is the number of integers less than Q that are relatively prime to Q. And P minus 1 times Q minus 1 is the number of integers less than PQ that are relatively prime to PQ. All right, that's not an obvious fact, but it happens to be true. All right, now, find a large random integer E. This is step C. Find a large random integer E that's relatively prime to M. Now, M's not a prime, but I can still find integers that are relatively prime to it. Now, you can do this by guess and check. You can guess a large integer E, and then if it's not relatively prime, then guess another one. And actually, you usually can find one fairly quickly. It's quite common to find numbers that are relatively prime to each other. Okay. Now, once I have the number E, and it's relatively prime to M, then we've seen that it's possible to solve such an equation, DE congruent to 1, mod M, for the unknown D. All right. Recall that this equation is the same thing as saying DE is equal to 1 minus, let's say, FM, where D and F are unknowns. And that's the same thing as saying DE plus FM is equal to 1. And we've seen that as long as E and M are relatively prime, in other words, if the GCD of E and M are relatively prime, is equal to 1, then we can find D and F. Okay. Now, if you have very large numbers, it may take a while, but it is possible to find a D such that DE is congruent to 1. All right. Now, here's the way it works, and we'll see later why it works. So suppose in this case we have Jennifer who runs a boutique, and she has a customer whose credit card is X. Right? So first, Jennifer's computer sends the numbers E and N. So this is the public key. Okay. Now, if the customer has E and N, then the customer can compute X to the E mod N. Customer then sends the result to Jennifer. Jennifer can recover X by computing Y to the D mod N, where Y is the message she receives from the customer. And D and N, the D is a secret key. Or private key. Okay, this paragraph reinforces the nature of D and E. E and N are sent out openly. Everybody knows those. The only thing that nobody knows is D. Now, why? And it's hard to find D because people need both E and M to find D, and nobody knows M. So M and D are known only to Jennifer. Okay. All right, so here's one example of how the process works. All right, so for instance, suppose we have a message which is in numerical form as 395. We've seen how we can turn alphabetical information into numerical information. Okay, so suppose our numbers P and Q are 23 and 29. Now these are far too small to be practical numbers. As we said above, people typically use 150-digit primes, but these are small enough to see what we're doing in the process. Now, according to the process, first we have to compute PQ and P minus 1 times Q minus 1. All right? The next step in the process is to find a number that's relatively prime to P minus 1 times Q minus 1. So by trial and error, we can find 487, which is relatively prime to P minus 1 times Q minus 1. Right, this number here, 616, was P minus 1 times Q minus 1. Okay? Then according to the prescription, the encoded message is this message. This was the message. So this is the plain text. The 395. The 487 was the public key. And the 667 is N, so that's also public. Okay. And you compute this result, 570. Now, this may seem like a long computation, but there are ways of quickly raising numbers to large powers, and we'll see that following this discussion. Right, now, once we have the public key E, remember that part of the process is to find a D such that DE equals 1. And we can use a Euclidean algorithm to show that 191 works. We're skipping the details here. And that means that my D is 191, and I use the same N, which is 667. Okay. All right, now according to the prescription, all I have to do is take my received message, which is 570. So this is received. I raise it to the secret key, and I take the mod N, and this is the original decoded message. Okay, so you can see how the algorithm actually works. All right, now what's going on here? All right, so let's pull apart some of the mathematical relations we have with these numbers that we've created. All right, so first of all, we know that DE is congruent to 1 mod M, and we know how to write that as an arithmetic equality. DE is some multiple of M plus 1. All right, now, if Y is the received message, remember that Y was found as X to the E. So Y to the D is X to the E to the D power. And that gives me X to the DE power. And DE is Km plus 1, which is X to the M to the K to the N, K, X times X. So we're just using exponent rules here. Now it turns out there's a very deep and beautiful fact about numbers, that if M is the number of positive integers less than n that are relatively prime to n, then x to the m is congruent to 1 mod n. Okay, so if I take this number here and I find out what it is mod n, well, x to the m is congruent to 1. So that means that this x to the m, if I'm talking mod n, I can replace this x to the m with 1. So I have 1 to the k times x. That means that my y to the d is actually congruent to x mod n. Okay, so that shows how when I do all these operations and I send y and I take y to the d power, take it mod n, I'll return with my original message. Okay. Now, what would be required to break this system? In order to find d, you need to be able to factor n and solve for d. But if you can't factor n, then you can't find d. Okay. Here's an exercise to show that if p and q are primes, then the number of positive integers less than pq, relatively prime to pq, is p minus 1 times q minus 1. Let's just do a simple example. For instance, we have to take 2 primes, so I can take p equal 2 and q equal 3. So here we have 1, 2, 3, 4, 5, 6. Well, I'm sorry, it has to be less than 6, so we only go up to 5. How many numbers here are relatively prime to 6? Well, 2 is not, 3 is not, 4 is not. We have 2 numbers. And we can check that 2 is equal to p minus 1 times q minus 1 equals 1 times 2. Yes, that works. Okay, so you can try that for other larger primes, but in fact this is generally true as long as p and q are both primes. All right, this section I'm not going to talk about in detail, but suppose that you have 2 people communicating, Alice and Bob, and Alice wants to make sure the message actually came from Bob. In this RSA system that we've been talking about, the recipient who has the secret key can't tell who actually sent the message. If she wants to make sure it actually came from a particular person, then you have to do some additional encryption. So this shows how if Alice and Bob both have secret keys, then they can find ways to guarantee the authenticity of messages. In other words, Alice can receive a message and make sure it actually did come from Bob. So you can read this, how those 2 secret keys can be used to do the encoding.